There are two kinds of uncertainty that economists deal with. More often, and the kind we're going to deal with in this class, we're dealing with risk. There's also another type that is, of course, incredibly important in the real world that we sometimes call radical uncertainty. With radical uncertainty, we're dealing with unknown probabilities. So if you put yourself into, say, the perspective of someone in 2006, that was the year before the iPhone was introduced. Back then, we all had flip phones. Trying to predict what was going to happen 5 years later in the realm of cell phones, you were very much in a world of uncertainty. Well, there had been some attempts at smartphones. There was the Palm Trio. There were Palm Pilots that weren't actually cell phones but did similar things. But the technology just wasn't there and the culture wasn't there. We hadn't seen it. It was an unknown unknown. So in that world, if you're trying to make a guess about how successful will Apple be, well, you're dealing with, maybe they introduce this product and it's huge. Maybe they introduce it and no one cares. But you can't really add those numbers up because you don't know how likely any one thing is, right? Not in any meaningful sense. Now, strictly speaking, life is always in the realm of unknown probabilities. So that's why I've got this asterisk here. A lot of the times when we think we know the probabilities, really it's we have a good educated guess. So for things that have happened a bunch of times before, we can rely on estimated known probabilities for things like, say, insurance. If you want to insure your home, the actuary at the insurance company has some idea of the probability that your house burns down, given observable traits about that house and the neighborhood and yada, 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 right? All these different things go into something that allows them to make a reasonable prediction. Now, given that, we can then use the tool of expected values, which is a relatively simple thing. It's just saying, let's add up the value of our possible outcomes, which I'm calling x1, x2, and x3, and then the probability that each of those things happens. So x1 happens, there's some probability that happens. x2, there's some probability. x3, well, the probability has to be 100% minus the chance that we're here, minus the chance that we're here. Now we're going to deal with 1 instead of 100%. So 0.5 equals 50%, but 0.5 times something gives you the equivalent. Right? It's just a little bit easier to work with these ratios rather than these percentages. So let's use a simple example, something a little less complex than an insurance policy. Let's think about a lottery ticket, and then we'll use that to transition into another topic, which is present value. So if you get a lottery ticket, a popular lottery format gives you $1 million a year for life. And of course, if you lose, well, you get nothing. So let's start with a simpler version of this before we transition into how much is this really worth. And let's ask, how much would it be worth to get a ticket where you win $1 million? So for X win, we can substitute in $1 million. And then we have to ask, what's the probability that you win? The probability that you lose is going to be 1 minus that probability. And what you get if you lose, well, that's going to be 0. And hey, 0 is convenient here because it means we don't even have to bother doing this math. Our expected value is just the probability that you win times what you actually win. So to make this simple, let's just say your probability is 1 in a million. If that's the case, the expected value of this ticket is $1. So how much should you be willing to pay for this ticket? Well, lottery ticket isn't as simple as you buy it and you get money. Really, you're buying maybe a way to daydream, right? Some off chance that you get some big thing. So for you and me as consumers, we might say, maybe it's only worth $1 in expected value, and maybe the price is $2. So you know that you're not making money. You know that your expected value, when we subtract out the price, is $1. Expected winnings minus a $2 price means your outcome is -$1. It's not a good investment, but it might still be kind of fun to buy a lottery ticket every once in a while, right? You can't win if you don't buy it, and you can afford to lose $1. Not a big deal. But if we think about this from the perspective of the lottery commissioner, they're not doing it just for fun. There's no entertainment value for the people running the lottery. For them, they have to ask the question of, are they charging a high enough price? And if they're charging a price of $2, they are covering their expected value, or in their case, their expected cost. So all we're getting here is a probability weighted average, right? We're used to averages where we add things up and then we divide by the number of things we're observing. Here, we could think about it this way. If you sell 1 million tickets, right? Let's just indicate 1 million tickets with all these dots. Most of them you pay out $0, but every once in a while you get a winning ticket and then a whole bunch more zeros. So for the lottery commissioner, we could add up all of these. We get $1 million cost that they're going to have to pay. And then if there are 1 million tickets that we're selling, then their expected cost for any one is going to be $1 million times that probability that they have to pay out. So we could think of that average as adding up all these outcomes and then dividing by the number of outcomes. But it's a lot easier to just say the probability is 1 in a million, 1 in a million times 1 million. And of course, a more complex and more realistic lottery ticket would be something like probability of the grand prize plus probability of the medium prize plus the probability of the smaller prize. So they might have, say, a cost where they pay out $10, one where they pay out $1,000, and one where they pay out $1 million. And then we add up these multiplied by the probability that they have to make those payouts. So the probability is going to be much higher here for this smaller number, but because they're paying out more of these small prizes, that's going to impact their expected cost. So their expected cost, when we roll all this stuff in together, maybe it's something closer to $150, right? At $150, if the price is $2, they're still on average making 50 cents per ticket, right? So they're at least covering their costs. Now, let's ask the question about how much should you be willing to pay for a ticket that gives you $1 million per year. So let's start with a simplifying assumption. Oh, I don't need that. Let's just get the screen. Let's start with a simplifying assumption that you get an even $1 million at the beginning of each time period. So we're going to get one a year, and we get our first payment at year 0. So here's our payout in millions of dollars. And let's see, will this autocomplete for us? There we go. So let's just think about a ticket where you get $1 million for 10 years. Will this drag out nicely? No. Let's try this again. There we go. So if you're getting it for 10 years, you get year 0. We don't actually want year 10 in that case. So here we've got 10 rows, 10 years, $1 million for each year. Now, the people advertising this lottery, they're going to tell you this is worth $10 million. Now, the question is it really? And spoiler alert, it's not. So the way to think about how much is this lottery ticket really worth is to ask, how much money does the lottery commission need right now in order to pay out this $10 million over 10 years? So for the first year, the money they need now is obviously $1 million. But the money that they're going to need in 1 year, they need $1 million in a year, but they don't need the full $1 million now. They can put that money into an investment account and grow that smaller amount to the full $1 million after 1 year of interest. So let's make an assumption about an interest rate. Let's say we can get an interest rate of 5%, 0.05. Now, if we put $1 million and we put $1 million into a bank account and we let it grow with 5% interest, then we can ask, what is that money with growth? In the case of 1 year, we're going to have our initial investment times 1 plus the interest rate. So 1 plus 0.05 means that we are getting the initial $1 million plus 5% of $1 million to the power of the number of years that we're waiting. Oh, and I left out an asterisk. There we go. So let's take a look at our formula. We're saying this $1 million that we put away plus 5% interest to the power of 0 gives us $1 million. So if we take this and we drag it through, this is going to calculate some numbers. So let's plug in, let's say, 0.95. If we put in, ooh, forgot something. We need a $sign here so that we can conveniently drag this down. Notice what happened here. I copied this formula down a cell and it copied all its references down one row, which is good for the pink and the blue, but for the red, that's not what we want. So with the $sign, when we do that, take it back. Why are you? Okay, now it's still referencing A3. Oh, not A3, sorry. E2 is where we want this to stick, or rather E1. So $1, A3 without the $sign. There we go. So now we are taking $950,000. We're growing that by 5% interest for just 1 year, right? So when we do to the power of 0, like we've got up here, we're saying this whole thing to the power of 0, that is going to just be 1, right? Any number to the power of 0 equals 1. But this to the power of 1 says we're taking $950,000, we're growing it by 5%, and we're doing that once. Now, if we take that same value and we do it twice, now we're going to the power of 2. This is the equivalent of saying 1 plus E1 again. So when I undo that, we've got our old formula. When I redo that, we've got this new formula where we're just multiplying this term in parentheses by itself. So what this means is we start with $950,000 in the bank. After 1 year, we end up with $997,050, just shy of $1 million after 1 year. And then we grow that an extra year, and we're going to get 5% growth on top of that, and we end up with 1.04 million. So this 0.95 isn't really what we need to put away for that first year. It is a little shy of what we need to be able to pay out the $1 million that we owe to whoever wins our lottery. But it's more than we need to pay what we're going to have to pay them 2 years from now. Now the question is, how do we get this number to be the appropriate amount so that this will turn to $1 million? We want this to equal the payout that we're going to have. We want to put something away and then after some number of years have enough money that we can meet our obligations. And we'd prefer not to put more money than we need to into this so that we can use whatever resources we have for whatever is most urgent for us. All right. That said, in a world of uncertainty, if you're running an investment like this, well, it's an investment for you running a lottery. It's taking people's money if you are on the other side of this. But in a world of uncertainty, you might want to actually go a little bit above what you really need. So something like, let's call that 0.9, 0.85. So this would be not a terrible idea for how to run this. Right? Putting away these values gives you a little bit of buffer on this, right? So this particular setup, you put $1 million away that you know you're going to have to pay out immediately. You put $1 million away to grow a little beyond what you're going to need, but you're going to need to pay out $1 million in a year. You just get a little bit of interest on top of that. When we add all of this up, you can see that for the payment 9 years out, for that 10th payment, we need much less than the full $1 million. So here, without even getting into the math of it, we can see that this $10 million prize that's being advertised, we could achieve for less than $8.35 million. Like I said, life is uncertain. Who knows what's going to happen? So if you were running a lottery, it would be a sensible thing to kind of build a little bit of slack into your policy. Build a little bit of wiggle room so that if something bad happens, you're able to recover from it. That said, let's assume that away for simplicity's sake, and let's try to deal with the math of how to get this. And that's going to be a little bit easier on paper. So let me get my notebook ready again, and let's see what we've got here. So fundamentally, we're saying we're going to put something away now, right? So some initial investment, let's call that P for present value. And we want to get some eventual payout, which we'll call F for future value. And the way that's going to work is we're going to say future value is equal to the present value with interest. So R is our interest rate. So after 1 year, we're going to have P plus R times P. So 5% of P on top of the P that we have initially. And then over multiple years, if R stays the same, we're going to grow that, and then we're going to grow it again, and we're going to grow it again, T times T for time. Right? So how many years are we going to let this grow? Now, we can do a little bit of arithmetic to sort this out. We want to know how much do we put away now to get 1 million in the future. So we know we want 1 million equals P times 1.05 to the power of whatever time period. Right? So if we're looking for year 9, we'd plug in a 9, but let's just leave this as T for now. And then we can divide out 1.05 to the T, 1.05 to the power of T, and we've got present value equals, I'm going to plug back in future value here just for generality's sake. Future value over 1 plus R, 1.05 to the power of T. Right? This is a relatively simple equation, and the algebra was pretty straightforward too. Right? This I find really easy to remember. This I forget all the time, but it's really easy to go from here to here. So we've got our formula for present value, and I'll show you another form for this. We can call this also future value times 1 plus r to the negative t. A negative exponent is the same as putting it in the denominator of a fraction. So let's go back to our spreadsheet and let's get these details into here. So here we got 1 and we got 1. I'm going to leave this one alone for a second, but what I want is the future value, the $1 million, times 1 plus our interest rate, and Alt F4 is a hotkey to automatically cycle through these combinations of dollar signs. $E means that if I copy this formula to the right, it's still going to reference column E. $1 means if I copy this reference down, it's still going to reference row 1. So I need that. I don't need the $E, so I'll just stick with that. And then to the power with this caret sign, which is Shift 6, the number of years. So, oh, I made a little mistake, not to the power of 1, to the power of -1. There we go. So a little more than 0.95. Now if I drag this down, now I'm getting 0.81, and I've got the $10 million we need. I'm going to drag this up also just to be complete. So again, something to the power of 0, even -0, is going to give us $1 million times 1. So what do we see here? This $10 million prize only requires selling $8.1 million worth of tickets. So you can tell people that you're giving them a $10 million prize, but you're really only giving them a prize worth $8.1 million. That is how much you need now in order to make good on this obligation. Now, that is a little bit of a hassle. So what we did here is we calculated for each year, and then we added that all together. Let's go ahead and just introduce a little bit of notation for that on paper. So for this, we use the Greek capital sigma. This means sum. At least in this case, it means sum. And then we're adding from t0 up until t equals 10. So we're doing exactly what we did in the Excel spreadsheet. We're just adding up all those rows. In the bottom row, we start with what's in row 0, go up to row 10. And what we're adding up is the amount of money we need to put away in order to make the payout for each year. And that amount was our future value times 1 plus the interest rate to the power of -t. So when t is 0, like I said, we get $1 million times 1. When t is 1, we get $1 million divided by 1.05 to the power of 1. So $1 million divided by 1.05. And so on until we get up to 10. Right? So actually calculating this, you're just going through and manually doing these numbers. Right? So this is something you can do by hand. It's a lot easier to do it in a spreadsheet or something like R. Now, here's another question. What about the prize is $1 million per year forever? This is a good time to pause and think, how much should that be worth? Now, strictly speaking, we can still use this notation. Now we're just going to add up until infinity for f times 1 plus r to the -t. But this negative t is eventually going to be really, really big. So we're going to have $1 million over 1.05 times, not exactly times infinity, but times a very, very big number, which is going to be 1 over a really big number. 1 over a really big number is going to be at least approximately 0. Right? So as we go further and further into the future, this is our time traveler's dream. You go back in time 1,000,000 years and you put a penny in the bank, and then you come back to the present, and with compound interest, it's grown to $1 bajillion. If you sell a lottery ticket and say, I will pay you $1 million 1,000,000 years from now, you really don't need to put away very much money in order to make good on that contract. Now, in this case, we actually have some clever math that's going to make this a lot easier. I'm not going to run through the math specifically, but I will say that the YouTube channel Game Theory 101 does a really nice job of walking through this clearly and concisely. Here's the TLDR version of this. So the simplified version is we can just change the question. So our new question is, how much gives us $1 million per year in interest? So the temptation is to say $1 million a year forever means $1 million times infinity, which means infinite payoff. But a bird in the hand is worth more than 2 in the bush, and in this case we're thinking $1 million now versus $1 million 1,000,000 years from now. Obviously the present is worth much, much more, and because as we go further and further out in time, the present value of that future payment approaches 0, we actually do get a finite answer to this. So at 5% interest, we're going to need something that 1/20th of our initial amount is $1 million. And the math for that is as simple as this. We say $1 million, or our present value, really our payment, let's call that payment, divided by the interest rate. So payment over R, in this case, it's going to give us $20 million. You put $20 million in the bank. After a year, you're going to have $21 million. You pay out $1 million, and now you've got $20 million in the bank. For the next year, that's going to grow to $21 million. You're going to pay out $1 million. You're going to be left with $20 million. And you're going to let that grow to $21 million next year so you can make that payment again. You will have, with $20 million, enough that every year, with that 5% interest, you have $1 more million to pay out to the person who won your lottery. So there, you would be tempted to say, we've got an infinite prize. We will give you infinity dollars. You can pass this on to your heirs. You can sell it to some company you saw on daytime TV. It's infinite money, but it's worth a finite amount. It's worth $20 million. And this is really, I think, the coolest little thing in the realm of compound interest, this idea that we can take this simple equation where we know that with compound interest we grow some amount to some bigger amount, and we can do a little bit of algebra and ask, how much do we need to put away now to get that amount in the future? What is the present value of $1 million 10 years from now? With this, we're able to compress complicated stories about payments in the future and give us a specific number, something that lets us make a comparison. Is it better to get $1 million now, or is it better to get $2 million 10 years from now? We can make that comparison with this bit of math. All right, that's the big picture of all this stuff. Really what it boils down to now is practice. So let me come back to the screen and share, whoops, not this. share our formulas. So with growth, our future value, ignore row 13, but for 9 years out, we're going to take some amount of money, right, the money that we put into the bank in row C, column C, we're going to grow it with interest, 5% interest, 9 years, right? So we're going to start with some amount plus 5%, and then that amount, including the 5%, we're going to get 5% on that, and on and on and on, until finally we are able to get enough money that we can pay out $1 million. To do that backwards and get how much money do we need right now, we take this $1 million target that we've got. We want to have $1 million, and we divide it by the interest growth to the power of the time in order to figure out how much do we need right now. So in this case, 0.64 gives us enough now that it will grow to be $1 million in 9 years. And again, asking the question this way, how much money do we need now? That is fundamentally what we're doing when we're dealing with the issue of present value. We're saying we get $1 million in the future. How much do we need now to grow that money at some reasonable interest rate? That is the present value of $1 million 9 years from now. Or $1 million a year forever is actually even a little bit easier. How much money do you need to put away to get $1 million of interest every single year? $20 million at 5% interest is going to be enough. If we have a different interest rate, we're going to have a different answer. So say we had 10% interest. In that case, you only need $10 million. So the higher the interest rate that you have access to, the less valuable those future payments are, because the easier it is to get them. You get more growth at 10%. And so likewise, if we change this to 0.1 to 10%, this $8.1 million gets a lot smaller. You only need $6.75 million to get $10 million worth of payments. All right, keep at it. Look for practice stuff on Khan Academy. We'll talk about this in class, and I will see you in the future.